So let's begin with a brief history. The Open System Interconnection Reference Model is a conceptual model with two major components. The first main component of the OSI networking reference model is an abstract model of networking. It's a 7-layer model. The second major component is a set of specific protocols which allow differing computing systems to communicate with one another despite their different architecture. So why was a networking model required? Well, early networks communicated using proprietary languages. Because of those proprietary languages, early networks could only communicate with like systems. So an IBM network could only communicate with another IBM network. In addition to that, the US government desired a robust computer communication system that could survive disaster. The first networking reference model that was developed was the TCP IP reference model. The Transmission Control Protocol Internet Protocol reference model was published as the United States Department of Defense standard in 1982. All of the major systems manufacturers adopted the TCP IP reference model beginning in 1984. AT&T moved the Unix implementation of TCP IP to open source in 1989, further cementing TCP IP's place in networking. The OSI reference model came later than the TCP IP reference model. The OSI model was published in 1983, and it defines the relationships between differing protocols and hardware. It's time to move on to a discussion about the networking reference models in more detail. We're going to begin with the OSI reference model. It is a 7-layer reference model. Layer 1 is also called the physical layer. It standardizes the electrical signals that networks use. It also defines cable standards and how the bits of data are placed on the physical media. Network cables and hubs are part of Layer 1 of the OSI model. Then there's Layer 2, which is also called the data link layer. It's responsible for identifying the individual nodes, both the sending node and the receiving node. It also introduces an error correction method known as the frame check sequence, or FCS. Layer 2 is composed of two sublayers. The first of those is the logical link control layer. It is mainly responsible for flow control and error correction. Then there is the media access control layer. It is mainly responsible for node addressing. Switches and bridges are Layer 2 devices. Then there's Layer 3, the network layer. It's responsible for routing functions between networks. It also identifies networks and nodes on the network. Routers are Layer 3 devices. Then there's Layer 4, the transport layer. It's responsible for breaking the data into smaller pieces for the lower layers and for the actual data transport protocols, two of which are TCP and UDP. The transport layer may be required to confirm the actual delivery of the data stream, and it may be required to offer error correction. And it does this through the use of TCP, or Transmission Control Protocol. Then there's Layer 5, the session layer. This is the layer that is responsible for establishing the initial parameters between two systems. It sets up and tears down the communication channel. Layer 6, or the presentation layer, is responsible for taking data and converting it from a machine-dependent language to a machine-independent language. This is also the layer that has the main responsibility for encryption between networks. And finally, we have Layer 7, the application layer. This is the layer that is responsible for the protocols that request services or functions from other systems. These protocols may not be the actual application. For instance, Internet Explorer is an application that uses HTTP at layer 7 to request web pages. Now let's talk about the TCP IP reference model. This is a 4-layer reference model. The lowest layer is the network interface layer, which can also be known as the link layer. It handles electrical signaling, flow control, error detection, and node addressing. Then there's the internet layer. This layer handles routing functions and identifies network systems and nodes on those networks. Then there is the transport layer, which handles breaking the data into more manageable pieces for the lower layers. It is also the layer that is responsible for the delivery method, which can be either reliable or unreliable, and error correction for when reliable delivery is used. And finally, there is the application layer. This layer handles requests for services from applications. It also handles translation to machine-independent languages and encryption. It also sets up and tears down communication sessions between systems. So now let's do a comparison between the OSI and TCP IP reference models. While TCP IP is the dominant model, most technicians communicate issues using the OSI model because it is more specific. When a problem occurs, and believe me, they will, it is easier to resolve them with the more highly defined set of specifications of the OSI model versus the specifications of the TCP IP model. It's easier to resolve an issue at the session layer of the OSI model than it is to track down what went wrong in the application layer of the TCP IP model. Both the OSI and TCP IP models are reference models only. It is not mandatory that they be followed. Each developer and manufacturer determines its own method of implementing the reference models. While in theory there will never be a problem in communicating between devices and systems, remember, it is only a theory. I'm going to begin by talking about TCP and UDP. Before I can talk about TCP and UDP, we need to talk about the transport layer. Most networking models follow the Open Systems Interconnection Reference Model, or the OSI model. It is composed of 7 different layers, which include the application, presentation, session, transport, network, data link, and physical layers. The layers work together to create a system of communication that allows for different types of computing systems or networks to communicate with each other. Layer 4, also known as the transport layer, receives data from the session layer, which is layer 5, and determines what method or type of delivery is required for the data. The transport layer then hands that data with the instructions for the method of delivery to layer 3, which is also known as the network layer, which is then responsible for determining where the data is actually going. There are 2 main transport layer protocols. They are TCP and UDP. TCP, or the Transmission Control Protocol, is a protocol that determines the type of delivery method that will be used in network communications. TCP uses a reliable method to deliver network packets. TCP helps to set up the connection session. It helps to establish error control during the communication session, and it helps to tear down the communication session when it's done. Now, TCP does use a reliable delivery method. One of the main ways that it does this is through the use of a 3-way handshake. The first step of this handshake is the request for the connection. The second step is the reception of the response from the other end. The third part of the 3-way handshake is when the requester sends an acknowledgement back that sets the sequence numbers that will be used with every packet that is delivered. Every packet that gets sent must be acknowledged by the receiver. If the sender doesn't receive the acknowledgement of a packet, the sender will then resend that packet. All packets are sent and received in order. They're never out of order, or they should never be out of order. So now let's talk about UDP, or User Datagram Protocol. It's a protocol that determines the type of delivery method that will be used in network communication, just like TCP. Unlike TCP, UDP uses an unreliable method to deliver network packets. It does not help to set up the connection session. It does not establish error control, and it does not help to tear down the communication session. It uses an unreliable delivery method. This could better be described as a best effort delivery method. It sends the data stream to the destination, trusting that the destination is A, listening for the data stream, and B, willing to accept that data stream. The data stream flows with no acknowledgement of it being received. That's how UDP works. Not all communication can be treated the same. That is why there are both reliable and unreliable delivery methods. With TCP, the sender can be assured that the other end of the line has received all of the packets that were sent and that the packets were received in the proper order. This works well for communication that is not sensitive to latency issues that are associated with the overhead of reliable deliveries. UDP strips off the overhead but sacrifices reliability. It is well suited for network communication in which speed is more important than reliability. When using voice over IP, it is more important for the flow of packets to be continuous than for communication to be held up while waiting for packets to arrive in the right order. Voice over IP communication can survive the occasional dropped packet, but it gets very miserable when it has to wait for those packets to arrive. Now let's move on to ICMP. The Internet Control Message Protocol works at layer 3, which is also known as the network layer, of the OSI reference model, and it is used by IP, or the Internet Protocol, to perform several services. As a messaging service for IP, ICMP packets are carried as encapsulated IP datagrams. It provides information about network issues. The ping utility uses ICMP to test for end-to-end connectivity between two devices using ICMP echo request packets. The traceroute utility uses a combination of ICMP echo requests and destination unreachable packets to map the actual route between two endpoints. Also, if a router's memory buffers are full, it will continue to send out ICMP buffer full messages until the congestion has been reduced. This allows the other routers to slow down their transmissions to avoid packet loss.